Okay. Oh, are we on that? Okay. Hey everybody, how's it going? So we're going to have some fun because we're going to talk about exponentials and logs together. In essence, we're going to connect the two. I know you've done a lot of work talking about learning how to use logarithms. Today, we're going to learn where logarithms come from. Specifically, they are the inverses of exponentials. And so we're going to talk about the algebraic properties of logs and where they came from, because they're super weird. They come from the properties of exponentials. And then we're going to introduce a big important thing called the change of base formula for exponentials. I know that we have a change of base formula for logs, but there's an additional one for exponentials. And once you know that logs are inverses of exponentials, it all comes together. So let's just start from scratch. There is a relationship between logs, functions, and exponential functions. If you have a function 2 to the x, and you have another function log 2 to the x, you must have realized now that these ones are super related. And the reason you should be at least aware, at least conking yourself on the head, that the two are related, it has to do with the power rule. Do you remember the exponent rule for logarithms? It goes like this. Log 2, if you have a number to another power, you can rewrite this as n out front log 2 of a, right? And there was the same base rule, right? Which said that log 2 of 2 is equal to 1. Anytime you input the same number into the logarithm function as the base, you get 1 out. In combination, these two, they do something really fun to exponentials that have the same base. If I have, say, log base 2 of 2 to the 4, you can rewrite this as 4 times log base 2 of 2, which is equal to 4 times 1, which is equal to 4. In other words, if the base of the exponential inside the logarithm when you're building a composite function matches this base, then the outcome will be whatever this exponent is. It's going to be the same number. And the really fun thing about this is that you might recognize that this is an attribute. So this is a composite function. Where I've taken the g of x function and I've put the f of x function inside of it. And because of these two properties, let's just make some space here. Because of these two properties together, if I take the g of x function and I put the f of x function inside of it, you can write this log base 2 of f of x, which in turn becomes log base 2 of 2 to the x, which in turn becomes x times log 2 of 2, which becomes x times 1, which becomes x. Just like when we were talking about inverse functions, if we put one function inside of another function, you get back the input to the first one. That means they're inverses. They are inverses. Now, I haven't just proved that they are inverses. So there's a thing, okay? Before I go on any further, there's lots of different types of logs, right? Log base 2 of x is different than log base 10 of x. And there are lots of different exponentials. 2 to the x is a different exponential function than 10 to the x. And the deal here is that they're paired off. Okay? So log base 10 to the x gets me back x. Log base 2 of 2 to the x gets me back x. But log base 2 of 10 to the x, according to that power rule, you rewrite this log base 2 of 10, that's not the same. Here, let me calculate that. Ln of 10 divided by ln of 2. So this is equal to x times 3.321928 ... Okay? This number isn't equal to 1. So even though these are inverses of each other and these are inverses of each other, it doesn't go the other way. They're only the inverses. Log a of x is the inverse of a to the x if the bases are the same. Okay? So that's super cool. Let me write this out a little bit more formally. The logarithm function log base a of x and the exponential function a to the x are inverse of one another. And that means that log a of a to the x is equal to x, but it also means that a to the power log a of x is equal to x. They're proper inverses. Okay? So for instance, you go, okay, log base 2 to the 3 is equal to 3. On the other hand, 2 to the power log base 2 of 4 is just whatever is the input to that. That's equal to 4. Before we go on, do you want to try a couple of these? Let's do a little activity. So the answers are either, I want you to write the answers as a number or the phrase not inverses. Okay? So for instance, log base 3 of 3 to the 4, that output is going to be 4. 7 to the power log base 7 of 2, that's going to equal 2. Okay? Log base 2 of the power 7 to the 3 is equal, I want you to write not inverses on that one because the bases are different. That's the activity. I want you to recognize whether or not the bases are the same, so they are inverses, and if they are, evaluate them, and if they're not, just write not inverses. So let's try some. Ln e to the 4, log base 10 to the 7, e to the log base 3 of 5, 2 to the log base 2 of 4, and then 4 to the log base 3 of 4, and then log to the 3 of 3 base 4. Okay, try those ones. If they are inverses, write down the number, and if they're not inverses, say they're not inverses. This activity is really helpful a little bit later. It's important to be able to recognize when there are inverses because the answer is really easy to find. Okay, ready? Remember that ln is log base e. Okay, So they are inverses. 4. 10, 10. That's the same. The answer is 7. 2, 2. They're the same. So the answer is 4. 3, 3. Those are the same. So the answer is 4. E is a different number than 3, so they're not inverses. We can still evaluate that number, by the way. You can take out your calculator and calculate it. It's just that they're not inverses. And then this one, 4 is different than 3, so this one is not inverses. Okay? So the long and the short of it is, it's really helpful to recognize which ones are inverses of each other, and then run from there. Okay, so it's not a coincidence that logs and exponentials are inverses. In this big world of math, sometimes these coincidences happen, and you're like, wow, or sometimes there's like an underlying structure. In this case, they're inverses because that's the way they were designed. And you might be wondering why I went through all of this thing. Well, let's the short why I didn't tell you this sooner. I didn't tell you it sooner because it's really important to be able to manipulate logarithms on their own. To think of them as their own thing instead of thinking them as, you know, just special functions that are inverses to exponentials. Because in Math 100, you're going to be using logarithms as their own functions. But let's talk about where logs come from. So it's super usual to find systems that have exponential behavior. The number of cells in my petri dish are y is equal to 2 to the t, where t is in hours. Okay, so that's an exponential function. At time t is equal to 1, there's 2 cells times equal to 2, there's 4 cells, and it doubles and doubles and doubles. Okay, so we can use this model in a variety of ways. For instance, you can ask questions like, how many cells when t is equal to 3? How many cells are there on the third hour? How do I answer that? I just plug it into the function, 2 to the 3. Get out my calculator, 2 to the power 3, and the answer is 8. There's 8 cells. On the other hand, there is a class of questions that uses this model in a slightly different way. And it might ask, at what time are there 16 cells? At what time are there 26 cells? How do we answer these questions? These problems are so prevalent, these types of behavior, these models are so prevalent that we often want to know how to answer these questions. Well, let's focus on the first one right now, because we can probably figure out its answer. You can figure this one out by trial and error. So you can be like, okay, 2 to the 3 is equal to 8. Let's try 4, 16. Oh, look. When t is equal to 4, the output is 16. Cool. So the answer to this question is 4 hours, there's 16 cells. So that's fun. Trial and error. How do we trial and error the second question? At what time are there 26 cells? So what you do is you go, well, I don't know. How about t is equal to 4, so y then is equal to 2 to the 4, so that's 16. What about t is equal to 5? 2 to the 5, so that's 32. That's too much. Then t is equal to 4.5. Y is equal to 2 to the 4.5, and you get out your calculator, and you calculate that, and that's 22.62. That's too small. We want 26. So t is 4.7. Y is equal to 2. 4.7 is equal to, all right, 2 to the power 4.7. 25.992, but that's not quite 26. All right. So you're bored of watching me try trial and error yet? So the only way to solve this problem is actually literally what I just did, trial and error. But like I said, these problems show up so frequently that to help us along with these problems, people started making tables of outputs, right? So like, for instance, calculating 2 to the power 2.5, that's equal to 2 to the power of 5 over 2. And so that's like square root of 2 to the 5. So that's the square root of 32. Calculating that's not easy. I mean, you can do it. There are algorithms. I haven't taught you any of them, but there are algorithms for calculating square roots. So what people did essentially was they just started making tables of these, and they were like, okay, when t is equal to 2.4, t is equal to 2.5, t is equal to 2.6, t is equal to 2.7, t is equal to 2.8. And for each of these, you just calculate the output, 2 to the 2.4, so that's 5.278. And t is equal to 2.5, that's 5.6568, and 2.6, that's 6.06286, and 2 to the power 2.7, that's 6.498. Oh, is that? All right, well, that's fine. So where was I? 2.01, and then 2 to the power 2.8 is equal to 6.96444, right, etc. So what they would do is they'd make these huge tables. And what these huge tables would do is it would help you calculate these weird intermediate values that weren't easy to calculate. So this table here represents 2 to the t, right? And then, so that would help you do questions like this. So if somebody was like, hey, when t is equal to 2.4 hours, how many cells are there? And you would go like, oh, I don't know, and you'd go look it up on your table. Okay? So that answers kind of, that makes answering these types of questions easier, but it also makes answering these types of questions easier, because what you can do is you can take the same table and you can write it backwards, right? So if the input's always on the left, oh geez, that's not what I wanted to do. And then the value of t is always on the right. You can make a table that looks like that. And this is the inverse of the original function. And then what you can do is you can look up your number of cells in this column somewhere, and that will tell you at what time it happens. Okay? So that is literally a brute force way of solving this problem. I made a table, and that helped me build an inverse table, and then I could just look up my answers. And so we needed to give these inverse tables a name. So what we did is we gave them a name. We called these tables logarithms. Log 2 of y. Okay? And that's literally where logarithms come from. They're just the inverses of exponential tables. Which is essentially why they have all these inverse properties. It's because they're literally the inverses. This is where they came from. This is the origin story of logarithms. So consequently, people discovered all of the different algebraic properties of logarithms. Okay? So, you know the origin story now. It's just a table. It's the exponential table, and then you just flipped it backwards. Great. So what? So we know, I mean, the first thing I taught you was that there's a whole bunch of properties of logarithms, right? So log of a m times n can be written log a of n plus log a n. And log a m over n is equal to log a m minus log a n. Where do these come from? Where do these properties come from? We know that they have the weird algebraic properties. Where from? Well, we also know that exponentials have weird algebraic properties, right? You multiply two exponentials with the same base together, and you just add their exponents. If you divide exponentials, you get a n minus m. You might have found it strange, and I did make a note of it, that multiplication becomes addition, multiplication becomes addition, division becomes subtraction, division becomes subtraction. It's not a coincidence. I explained where these properties come from, and that should have made sense to you. These properties, on the other hand, these algebraic properties, they come from these algebraic properties. They come from the fact that logarithms are inverses. So I can show you now, we've talked enough about it, that I can explain to you now where all of these laws come from. In other words, if I assume that you didn't know any of them, and who knows, maybe you still don't, I can tell you essentially why they're true. So let's forget that these are true. And just forget all about these. Forget. Suppose somebody came up to me and they said, hey, if I have a logarithm, base a, okay, and I have two numbers, call it p and q, and I multiply them inside the logarithm, is there anything interesting I can do to those expressions? Can I simplify this at all? And what I would argue is I'd say, okay, well, let's write p as a to some power, and q as a to some power. You might be wondering why I'm doing this. I mean, okay, so let's suppose that p is equal to 4, and q is equal to 32. I want you to note that the base I'm changing to is the same base as the base of the logarithm. I can write this as 2 to the power 2, and I can write this as 2 to the power 8. So essentially I'm just doing that. Instead of describing it as just some number, I'm describing it as 2 to some other number. Instead of writing this as a number, I'm writing it as 2 to some other number. But that's it. It's a simple change. I want you to then note that p times q is then a times n times a times n. And because of the properties of exponentials, we can write this expression as a n plus m, right? And so your log a p times q, you can just rewrite this just okay, log a to the n plus m. You know that this is just some constant number. You can bring this out front. Because they are inverses, because they have the same base, this just becomes n plus m. And then you note something else. You note that the value of n is equal to log base a to the n. You note that m is equal to log base a to the m. In other words, log p and log q, right? And so what you can do is you can replace in this expression for n and m. Log a p times q is equal to log a to the n plus log a to the m is equal to log a of p plus log a of q. I did that assuming very little of this system. I think I might have assumed that you assume kind of that p and q are positive numbers, and that so that a is a positive number. But aside from that, like, I haven't really made any assumptions about the system. And so the result is, anytime I have two numbers that are multiplied together and I take the log of it, you can write it as the log of one times the log of another. I've just emphasized what we did. I told you to forget about this particular equation. Oops. I told you to forget about this particular equation, and then using only this plus the properties of inverse functions, you can rewrite this as causing this term. And similarly, you can do the same thing to show that this one turns into this one. Let's try that now. Incidentally, what I'm doing right now, it's called the derivation. It's a type of proof. So log of a, p over q. Okay? So first, write p as equal to a, same base, power m, and q is equal to a to the power n, where m and n are just some numbers, right? So if p was equal to, you know, I should. Okay, so for instance, log base 3 of 27 over 9, you can write p, which is 27, as 3 to the power 3, and q, which is 9, as 3 to the power 2, right? So p over q is a of m over a of n, and using the properties of exponentials, you can write it as this. Let's take its logarithm. They have the same base and they're inverses, so this becomes whatever the number is in the exponent, because they're inverses. And then you note that m is equal to the log a to the m, which is equal to log a of p, and n is equal to log a of a to the n, which is log a of q. And so the result here is that you can substitute these two back in and say log a of p over q is equal to log a to the m minus log a to the n, which is log a of p minus log a of q. Okay? In other words, using only a little bit of algebra, starting with this rule, and then using the idea of inverses, I was able to prove that this argument is true. And so these things are both properties of logarithms, but they come from these properties of exponentials, which should already make sense to you. Okay, well, before I go on, there were two other sides to these triangles, right? Like there was one over here that was like n times log a of b is equal to log a b to the n. I had another one over here that was like a to the n times m is equal to a to the n times m, right? Are these two related? Does this one come from this one? The short answer is yeah, but to prove that, we have to take a little detour to a very useful and important point. Ready? We have to talk about the change of base formula, technique for exponentials. I want you to remember that, log A of b, I can change the base of this logarithm. Let's say you want to evaluate things on a calculator. You don't have, log 2 of 7. You don't have a log base 2 function on your calculator. But what you can do is you can rewrite this expression in terms of a different base that you have. Right? So if you want to, you could go ln of 7 divided by ln of 2. And this is actually super important and super useful because you don't have a logarithm table for each and every single function out in the wild. Just ln and log base 10. Is there a similar strategy for exponentials? Can I change the base of an exponential? The answer is yeah, I can, and easily. I mean, like even if you don't know anything about it, you can still argue that it's possible. Like, consider this: 3 to the power 8. 8 is 2 times 2 times 2, and we know that anytime you see multiplication in the exponent, that it indicates that you can rewrite this like 3 to the power 2 to the power 2 times 2, right? So 3 to the power 2 to the power 4. What's 3 to the power 2? 9 to the power 4. Right? Alternatively, if I wanted, I could have rewritten this as 3 to the 2 times 2 to the power 2, which is 3 to the 4 to the power 2, which is 81 to the power 2. Which is fine. I mean, these all correspond to the same number. Let me try on my calculator. 3 to the power 8, that's 6,561. 9 to the power 4 is 6,561. 81 to the power 2 is 6,561. Okay, so it's the same number each time, which shouldn't surprise you. But thinking about exponential functions, this is actually pretty cool, because this exponential function and this exponential function and this exponential function all have different bases. So it's possible to write the same number as different exponentials if the base changes and the exponent changes. Right? So when 3 became 9, 8 became 4. When 3 became 81, 8 became 2. So the question when we're talking about changing the base isn't, is it possible? The question here is, how do I change the exponent? Let me write it like this. 2 to the 7, maybe not 7. 2 to the 6 is equal to 4 to the that. What does the exponent change to? What does the exponent change to? Well, I note that 2 to the 2 times 3 is equal to 4 to the question mark. And you can write this as 2 to the 2 to the power 3, 4 to the question mark. And so that's 4 to the 3, 4 to the question mark. So the answer is 3. This number should be 3. Well, that's neat. But that only kind of worked. I mean, I was only able to do that because I knew that 2 to the power 2 is equal to 4. Am I able to do it if I'm like 2 to the 6 is equal to 3 to the... What do I put up there? I mean, I don't know of any power 2 to the power that turns it into a 3. How do I can't break up the 6 in terms of that in a way I could before. But even then, this is actually a pretty cool idea. The idea is that I change the base, right? Go from 2 to 4, and in changing the base, I change the exponent. I'm going to teach you how to do that. To take a shot at this, we need to remind ourselves. Exponentials and logs are inverse. That means that 2 to the log base 2 of 4 is equal to 4. And 3 to the log base 3 of 21 is 21. So here's how the trick goes. Suppose somebody goes, okay, 2 to the 7 is equal to 7 to the... It's not 2. That'd be great, but it's not. What's that? What do I put up here? What I'm going to do, follow the following steps. First, I'm going to rewrite the expression. And I'm going to put the 2 in parentheses. Okay. And then I'm going to use exponentials. I'm going to write 7, because I want it to be 7, to the power log base 7 of 2. In other words, I'm just taking this 2 and I'm rewriting it in a different way. But I'm rewriting it in a different way so that this is now the base. I want 7 to be the base, so I make that the base, so then the base of the log has to be 7. It's equal to 7. And then the result is log base 7 of 2 times 7 is equal to 7. And that tells me what the number has to be. Okay? I can calculate this on its own. 7 times ln of 2 divided by ln of 7. What does that give me? Ln of 2 divided by ln of 7 times 7. So the answer is 2.49345. So apparently 7 to the power 2.49345 is pretty much 7. Let me calculate that. I'm going to use my calculator. 7 to the power 2.49345. What did I do wrong here? Ln of 7. Oh wait, hold on. Whoops. Okay. Just in the way I set it up. So apparently 7 to this weird number is equal to 2 to the power 7. So 2 to the power 7, I can calculate that on my calculator. That's 128. I can also calculate this beast on my calculator. So I'll do that. 7 to the power 2.49345. And that's equal to 127.9999. Yeah, that's close enough. Okay. So that's the trick. Let's review. Change of base. Somebody gives me an exponential and asks me to rewrite it as b, some other number, to some power. And they ask me what the exponent is. We do it in 3 steps. First step, you put a parentheses around the a. Second step, you rewrite a as b to the log b of a. According to the inverse property, that should be equal to a. This number is the same as that number. I've just written it in terms of an exponential base b. And the result will be b n times log b of a. That's my answer here. Okay? That's the change of base formula for exponentials. I'm going to be using it a bunch. So, why don't we try a few, huh? Actually, I say in my notes that I rewrote this. I should rewrite it a little bit nicer. So this is a to the b is equal to c, some other base, b times log c of a. Change the base. That's going to match the new base. That number is going to match the old base. Okay? So let's practice why don't you pause the video after I finish copying this out and figure out what goes in the blanks. There's some weird numbers that go in the blanks. Try it yourselves. Pause that video. Give it a go. Alright, well, let's unpause the video. Let's try it ourselves. 2 to the 4, that becomes 2 to the 4, which becomes 4 to the log base 2, base 4, oh jeez, this writing's too small. Which becomes 4, the new base, log 4 of 2, all to the power 4. So it's 4 to the log 4 of 2 of 4. Let me try calculating that. That's ln 2 divided by ln of 4 times 4. So this is equal to 4 to the 2. That's fun, right? Let's try the next one. 3 to the 7. Put the 3 in parentheses. Rewrite it with base 9. So this is equal to 9, 7 times log 9, 3. So 7 times ln 3 divided by ln of 9. So this is 9 to the 3.5. Let's try the next one. These next ones are going to be pretty irrational. 6 to the 2. Put the 6 in parentheses and then rewrite it base 4. So it becomes 4, 2 times log base 4 of 6. So ln of 6 divided by ln of 4 times 2. So this is equal to 4 to the power 2.58496. So incidentally, that number is 36. Let's see if what this number is. 4 to the power 2.58496. That number is equal to 35.9998. Alright, good. Yeah, that's pretty much the same number. Let's try the last one, eh? 21 to the 3. So put the 21 in parentheses. Rewrite it base 2. Log base 2 of 21 times 3, which is 3 times log base 2 of 21. 3 times ln of 21 divided by ln of 2. So this number is 13.17695, which is weird. Anyway, what's 21 to the 3? That's 9261. This value here is 2 to the power of 13.17695. 9260.98543. Fun, right? Okay. I'm going to assume that you are now pretty good at using the change of base formula. I made a promise at the start of this, though, that I would explain how this rule turned into this rule. Let's do that derivation right now. log A b to the power n. I want to prove that this is equal to log A b. So I don't know that that's true. I'm going to forget that that's true and start from scratch. Okay. First step, I'm going to use change of base. B to the n is equal to A log base b of, ooh, wait, I did that wrong. Log base A of b to the power n. So b to the power n can be rewritten with base A as n times log A of b, right? So this becomes log A of A n times log A b. And note that even though this looks super weird, it is just a number. And they're inverses. Log A and A to the power n are inverses. So I can rewrite this as n times log A of b, but that's from the inverse property of logs and exponentials times 1, right? So essentially all I've said is this term is equal to that term using the change of base formula, which is equal to that term. And that's why it's true. All right, so now you know where all these weird log properties come from. Let's review because there was a lot to chew on there. Okay, first off, properties here. Logarithm, base A, and the function a to the x are inverses. They both have their own properties, but the properties of the two are related because they cancel each other out. From these two, we ended up with the change of base formula. And then I want to, here, I'll just write out the medicine wheels of all three. This one went m over n is equal to a n, the m circle. A to the m times a to the n is equal to a m plus n. A to the m divided by a to the n is equal to a m minus n. And a to the n all to the power m is equal to a n times m. Those are the exponentials medicine wheel. Here's the logs medicine wheel. Log a of p times q is equal to log a of p plus log a of q. Log a of p divided by q is equal to log a of p minus log a of q. Change of base formula. Log b of a is equal to log c of a divided by log c of b. And then there was the log a of b to the n is equal to n times log a of b. Okay, so here's the idea. These properties, these algebraic properties of exponentials, those come from reasoning. we argued for why they are the way they are. We argued that this has got to be true. We argued that this has got to be true. We extended to negative exponents so that that one was true, right? So all of the different algebraic properties of exponentials come from direct reasoning about how exponentials should work consistently. It turns out, now, I told you guys all about these, and you had to learn about them independently because it's important to be able to operate with logarithms independently of exponentials. They literally show up everywhere in science. But the story is that logarithms and exponentials are inverses of each other. Acknowledging that they're inverses actually opens up a whole new set of skills. One of them is the change of base formula for exponentials. I'm now not stuck in any particular base. Any exponential I have can be rewritten in terms of any base I want. If I only care about the natural base e, I can write any logarithm function in terms of base e, right? Do you see what I'm saying? I'm saying, okay, somebody goes 2 to the x. If I want to, if my calculator only has base e, and some of them do, if you look around, your calculator probably has a function like that. How do you deal with it? The deal here is that you can rewrite this expression using the change of base formula as e ln of 2 times x. We have a change of base formula that really unlocks a whole new area of talking about things. The base of an exponential isn't immaterial. You can change it. You can modify it as long as you use this change of base formula. Okay? So recognizing that these two are inverses allows us to change the base of our exponential. It's a huge consequence. But in addition to that, it explains where all these bonkers properties of logarithms come from. This one, this property of exponentials turns into this property of logarithms. This property of exponentials turns into this property of logarithms. This property of exponentials turns into this property of logarithms. What about the change of base for logarithms? You can argue that straight up. And we did argue for how and where that came from on its own merits. Okay? So that's it for them being inverses. It turns out that there's a whole new pattern of mathematics in here. And the consequences are going to be absolutely fantastic. We'll get to that in the next video.